Hello lovelies, in this video we're going to be going through your OCR-A AS Chemistry Paper 2 that we've written for 2024. So if you're doing the A level or the AS level, this is still brilliant revision because it's going to cover loads of content and we're going to teach you the exam skills that you need to use in the real exam.
The group 2 elements show interesting chemical and physical properties. The first and second ionization energies for group 2 elements decreases as you go down the group. The graph below shows the trend for the first ionization energies. Here we're asked to explain the trend observed in the first ionization energies of group 2 elements. So first things first here, we should realise that as we go down the group, the ionization energy decreases. So we need to understand why that is the case. So as we go down the group, the number of shells, of course, increases. Now the knock-on effect of this is that we're going to have more nuclear shielding as we go down the group, and we're also going to have a bigger atomic radius as well. Now both of those factors is going to have an effect on the strength of the attraction between the outermost electrons and that positive nucleus. So as the atomic radius increases and the shielding increases, the outermost electron is going to become easier to remove because there's going to be a weaker attraction between that outermost electron and the positive nucleus. And so those are 3 key points that we need to say to get our 3 marks here. Firstly, we want to talk about how the atomic radius changes and how it increases. Then talk about how shielding increases because it is a different factor. And then link it back to the attraction between the outermost electron and the nucleus. So now we're asked to write the equation for the second ionization energy of magnesium. Now, really important that we know how to do these. Because this is second ionization energy, we're going to make the Mg2+ ion. Now, each of these ionization energy just involves the removal of 1 electron, okay? So we're going to go from the Mg+ ion to the Mg2+ ion plus 1 electron. And a really important thing to do is you have to include the state symbols when doing the ionization energy equations. And that doesn't matter if they state to do it or not, it's a vital part of the ionization energy equation. So we need to know that both of the Mg+ and the Mg2+ ions are gaseous. So that's what we write down now to get our mark for second ionization energy equation. A test tube with a strip of magnesium had a solution of dilute nitric acid added to it. Construct the balanced equation for the reaction of magnesium with dilute nitric acid. Now answering this relies on us remembering our MASH equation, okay? Metal plus acid makes a salt and hydrogen. Now in this case that metal is magnesium. The acid is nitric acid, which is HNO3, make sure that you know that. Now magnesium is a solid, acids are aqueous, okay? So this is going to make our salt, and we should know that the salt that we make here is magnesium nitrate. Let's remind ourselves of how to get the formula for magnesium nitrate. We need to know that the nitrate ion is NO3-, and because magnesium is group 2, we should recognise that it's the Mg2+ ion. So as a result, when we want to write the formula of magnesium nitrate, we need to have 2 of the nitrate ions to balance the charge of the Mg2+. So the formula for magnesium nitrate is Mg brackets NO3 2 plus H2. And the salt is aqueous, and hydrogen, of course, is a gas, so that is a gas. Now let's just balance this. Don't forget to balance, okay? I can see because of the fact it's with magnesium, I need to have 2 nitrate ions. Now that means that to get those 2 nitrate ions, I need to have 2 nitric acids. Now by putting a 2 in front of the nitric acid, I've actually balanced the whole equation. So this here is my balanced equation, complete with state symbols to get me those 2 marks. So now we're asked to describe 2 observations which would be observed if calcium was used instead of magnesium. So to answer this, let's just remember where calcium is relative to magnesium in the periodic table. As you can see, calcium is below magnesium in the periodic table. Now what this means is that calcium is going to be able to lose its 2 electrons much more easily than the magnesium, because they're further away from the nucleus, and therefore there's a weaker attraction. This means that calcium is going to react more quickly than the magnesium will, because it's more reactive. So the result of this is going to be 2 observations. The first one is going to be about the gas that gets produced. It's going to get produced more quickly. So there's going to be more bubbles, and they're going to be produced at a faster rate. Now the second point is going to be that the calcium is going to dissolve more quickly than the magnesium would. Again, that's because the calcium is more reactive than magnesium. Magnesium can react with oxygen to form magnesium oxide. Here we're asked to name the structure of magnesium oxide. So to answer this, we need to recognise whether the magnesium and the oxygen in the oxide are metals or non-metals. We should know that magnesium is a metal and oxygen is a non-metal. And when those together, we form an ionic bond. Now the structure of things that are ionically bonded is always going to be a giant ionic lattice. And so that is our answer here. So now we're asked to draw a dot and cross diagram to show the bonding in magnesium oxide. And we need to show the outer electrons only. Well, we should know that generally magnesium has 2 electrons in its outer shells because it's group 2. Whereas oxygen is in group 6 and therefore it has 6 electrons in its outer shell. Now these are going to pair perfectly together because the 2 electrons that magnesium has in its outer shell can be donated, given up, to the group 6 oxygen. And therefore the oxygen will gain 2 electrons. Now the win-win factor in this is both of these are now going to have a full outer shell. The magnesium has a full outer shell because it's ditched the 2 that it had. And the oxygen is going to have a full outer shell because it's picked up another 2. Remember, these things will always take the path of least resistance, essentially. It's going to be much easier for the magnesium to lose 2 electrons than gain another 6 to get a full outer shell. And the same goes for the oxygen. It's easier for it to pick up 2 electrons than to lose the 6 it has. So these 2 team up perfectly. The magnesium is going to appear to have no electrons in its outer shell because it gave 2 up. We're going to put square brackets around it, and we're going to put a 2+ up in the top right-hand corner, and that represents the fact that it's lost 2 electrons. Whereas on the oxygen, we're going to put square brackets around that and a little 2- in the top right-hand corner to show that it's become a bit more negative. So next up, we're asked to compare how the electrical conductivity of magnesium with magnesium oxide would differ. And we're asked to explain why these differences are observed. So to be able to answer this, we need to think about the structure and the bonding in these substances. We should realise that in magnesium alone, we just have metallic bonding and a metallic structure. Whereas in magnesium oxide, of course, we have this giant ionic lattice. Well, magnesium always conducts electricity. And the reason for that is due to its metallic structure. Due to its metallic structure, it has delocalized electrons. And those delocalized electrons are always going to be free to move and to carry charge. So that is our explanation as to why magnesium will always conduct electricity. So now we need to go back to the magnesium oxide and ask ourselves, can this conduct electricity and why? So magnesium oxide can sometimes conduct electricity. It can conduct when it is either in a molten state or when it's dissolved and it's aqueous. Now the reason for this is because it has ionic bonds, and those ionic bonds are fixed in place when it's solid. Now that means that when magnesium oxide is solid, it cannot conduct electricity. However, when magnesium oxide is molten or dissolved, it has ions which are then free to move and to carry charge. It doesn't have the metallic bonding and the delocalized electrons that magnesium on its own has. It relies instead on its ions to carry charge, but those ions need to be in a state that enables them to be free to move, which is when it's molten or aqueous. The naturally occurring hydrated magnesium carbonate mineral, lansfordite, was first discovered in 1888 in a coal mine. It's found as a colourless or white crystal. Lansfordite, MgCO3.xH2O, was heated in a crucible. Here we're given some data and we're asked to determine the value of X, the waters of crystallization of this MgCO3.xH2O. So to do this, we're going to need to work out a few masses from this data. So I think the first thing that we should work out here is what the mass of magnesium carbonate is. And the way that we can do this is by taking the mass of the crucible and the residue after heating, so once we've heated and removed off all of that water, from just the mass of the empty crucible. So here I'm going to do 18.03 minus 17.36. And that gives us a mass for magnesium carbonate equal to 0.67 grams. So now that we know this mass, we can work out the moles of magnesium carbonate. Of course, before we do that though, we need to know what the MR is of magnesium carbonate. So we know magnesium has an MR equal to 24.3, plus the 12 for the carbon, plus 3 times 16 for the oxygens. Now that gives me an MR equal to 84.3. So now I can get the moles is equal to the mass, 0.67, divided by 84.3. And that gives me 0.00795 moles of magnesium carbonate. So now we know the moles of magnesium carbonate, what we can do is we can now work out how many moles there are of water. Or at least we can start by working out the mass of water. Now we can do this by taking the mass of the crucible plus this hydrated salt before heating and subtract from that the mass of the crucible plus the residue after heating. Because the difference between those two is going to be just the mass of the water that got removed when we heated it. So that means that the mass of water is equal to 0.72 grams. So now that we have that, we can work out the moles of the water. That's just going to be mass over MR. I know the MR of water is 18, but of course work it out if you're not familiar with that yet. So here I have 0.72 divided by 18, which gives me 0.04. So now we know the moles of magnesium carbonate, and we know the moles of water. Now to get what X is, what we need to do is work out the molar ratio between the magnesium carbonate and the water. So I've got 0.00795 to 0.04. And if I divide by the smallest of those two numbers, if I divide by the 0.00795, I should end up finding my ratio where the magnesium carbonate represents the 1. So here I get a 1 to 5.03 ratio where the X is represented as the number of waters, so that's what the 5.03 is representing here. And I've given that to 2 decimal places because that is what the question wants. Remember, after every single mathsy question, once you've calculated it, just go back, read the question one last time and see if they've stated the number of significant figures or decimal places that they want you to give it as. The student was presented with data on the time taken for 3 different primary haloalkanes, C4H9Cl, C4H9Br, and C4H9I to form a precipitate when hydrolyzed with water. Unfortunately, no colours were recorded, but the teacher said that they could still determine the identities of the haloalkanes. So we're given a table with data, and we're asked to use this data to identify which test tube contained 1-iodobutane. So what we should understand here is that the Ci bond is the one with the fastest rate of hydrolysis out of all the C to halogen bonds. So here we can identify that because it took less time for the precipitate to form, we must therefore say that 2 has the fastest rate of hydrolysis, and therefore 2 is 1-iodobutane. So now we're asked to describe and explain how the rate of hydrolysis changes as you go down group 7. And we already had to hit on this to answer A. We should know that as we go down the group, the rate of hydrolysis increases. So now we've described how the rate of hydrolysis changes, now we need to explain why that is the case. So the reason why this rate of hydrolysis increases down group 7 is because the CX bond gets weaker as you go down the group, and therefore less energy is needed to break that bond as we go down the group. So there we have it. That is our description and our explanation of how rate of hydrolysis changes as you go down group 7. A chemist carried out a 2-step synthesis to form a new substance from C4H9I. In step 1, KOH is acting as a nucleophile. Here we're asked to state what's meant by the term nucleophile. This is just such an important definition, so please do make sure that you learn this. A nucleophile is an electron pair donor. Don't know that, get writing it down right now and get memorising it. So now we're asked to draw the mechanism for the reaction occurring in step 1 to form substance E. So this is an example of a nucleophilic substitution reaction. So in order to do this, I'm going to start off just by drawing out my initial structure of C4H9I. And when doing this, we need to remember to draw on any relevant dipoles. So we should recognise that iodine is more electronegative than carbon, and therefore we're going to get a delta negative iodine and a delta positive carbon. Now we've also got the OH minus from the potassium hydroxide. That has a lone pair, and the electrons from that lone pair go to the delta positive carbon, and the electrons in the carbon-iodine bond go towards the delta negative iodine. By doing this, we simultaneously break a bond and make a bond. We break the bond between the carbon and the iodine, and we make a bond between the carbon and the OH. So when we break that carbon-iodine bond, the electrons move towards the iodine, giving us an iodine ion. And so there we have it, there is our mechanism. Now before we move on to the next part, I just want to give you a few top tips that will ensure you get all of your marks here. Remember that curly arrows show the movement of a pair of electrons. So they go from where there are electrons, so maybe where there are lone pairs, or where there are bonds, to where it's relatively speaking less negative. Make sure that when those curly arrows are leaving a bond, that they actually touch the bond. They're not just near the bond, they're actually touching it, because otherwise you may find you're not awarded the mark. Make sure as well that you include any dipoles in your diagram, because they will be looking for that to give you your marks. Here we're asked to draw the skeletal structure and name substance F. So first off, we need to remember what F is. Let's remind ourselves of this flowchart. So we form F when we take substance E and we reflux it with acidified potassium dichromate. Well, let's remember that substance E was a primary alcohol. We just looked at how we made that. In fact, we know it was butan 1-ol. Now, if we take butanol and we fully oxidize it using acidified potassium dichromate, then we end up making a carboxylic acid. In fact, specifically, we end up making butanoic acid. So that is the name of the substance that we make, but the question also wants us to draw its skeletal structure. So to draw the skeletal structure of this, we need to use the fact that we have 4 carbons, and so our zigzag region has to have 4 points to it. So there's our 4 carbons. Attached to the final carbon, we have a double bond O and an OH to show that carboxylic acid. So there we have the skeletal structure and the fact it's called butanoic acid. So now we're told that calcium carbonate powder was added to a solution of substance F. We're asked to give the name of the type of reaction that occurs when calcium carbonate reacts with F. Well, let's think. If we have an acid and we add a carbonate, we know from a long time ago that this is a neutralization reaction. In fact, this is a reaction we learned about at GCSE. So now we're told that effervescence was observed when calcium carbonate reacted with F. We're asked to identify the gas responsible for the effervescence and the test that could confirm this. Well, this comes back to what we know from GCSE again. We know that when an acid reacts with a carbonate, we form salt, carbon dioxide, and water. So we know that the gas out of these 3 is the carbon dioxide. We should also be familiar with how to test for carbon dioxide. And again, actually, this is something we learnt at GCSE, as well as at A-level. We should recognise that to test for carbon dioxide, we need to bubble the gas through lime water, and if that lime water turns cloudy, then we have carbon dioxide present. And so that there is our test for carbon dioxide. And that is that question finished. With many older cars still on the road, people are looking at ways to reduce their environmental impact without the need for expensive modifications. One example of this is that diesel-fueled engines can often easily switch to biodiesel blends without any changes being made to the vehicle. These blends are a mixture of usually 5 to 20% ethanol, with the rest being diesel. A car was filled with 50 litres of B5 biodiesel, which was a blend of 5% ethanol and 95% diesel. Assume that only complete combustion of ethanol occurs in the engine, as shown using this balanced equation here. We're told that the temperature and pressure inside the chamber is 2600 degrees C and 10 megapascals. We're told that 1 litre of ethanol has a mass of 786 grams. We're asked to calculate the volume of carbon dioxide in decimeter cubed forms from the combustion of ethanol present in this engine. So, to work out this, we're going to need to know how many moles of carbon dioxide are made. And to be able to work that out, first we're going to have to work out the moles of ethanol. Now, to work out the number of moles of ethanol, we need to know both the mass of ethanol and the MR of ethanol. So let's start with the MR. We know the formula is C2H5OH, which means we have an MR equal to 46. Now we're told the little fact here that 1 litre of ethanol has a mass of 786 grams. We're told right in the beginning of the question that we have 50 litres of this B5 biodiesel, and 5% of it is ethanol. So if we work out 5% of 50, we get 2.5. So we know we have 2.5 litres of ethanol here. So that's 789 times 2.5 grams. That gives me 1,972.5 grams of ethanol. So now I've got enough information to work out the moles of ethanol. I know that the moles of ethanol is going to equal 1,972.5 divided by 46. Now that gives me 42.88043478 moles of ethanol. Now, if I look at my balanced equation here, and remembering I'm being asked about carbon dioxide ultimately here, I can see I have a 1:2 ratio between the ethanol and the carbon dioxide. So that means to work out the moles of carbon dioxide, I just need to multiply the moles of ethanol by 2. Now that ends up giving me the moles of carbon dioxide equaling 85.760866956 moles. Okay, so big number. Again, I haven't rounded too early here because there's a lot of calculations, and if we round too early, then we're going to lose the accuracy of our final answer. So we're being asked about the volume, and we know that this isn't under standard conditions. So that means that we need to use PV equals nRT. And if we rearrange that to get the volume, we get moles times R times T over P. Now remember, we have to be very specific with the units we use in this equation. Temperature has to be in Kelvin and pressure has to be in pascals. And this is all going to give us a volume in meters cubed. So let's look at the temperature that they gave us in this question. In this question, we're told that the temperature equals 2,600 degrees C. Now, we need to convert that to Kelvin by adding 273. That gives me 2,873 Kelvin for the temperature. Now, for the pressure here, we've got 10 megapascals. We should recognise that mega means times 10 to the 6. So we have 10 times 10 to the 6 pascals. So now if we substitute in the moles, which is 85.76 and all of the other decimal places, and then we times it by 8.314, and then finally we times it by this temperature of 2,873. We divide all that by 10 times 10 to the 6, then we get our volume in meters cubed. So in this case, I find that the volume is equal to 0.2048 meters cubed. In this question, however, easy to lose that last mark, we need to give it in decimeter cubed. So we need to recognise that we can change from meters cubed to decimeter cubed by multiplying through by a factor of 1,000. So that gives us 204.8 decimeter cubed. And that is the volume of carbon dioxide that forms from the combustion of ethanol present in this engine. Some standard enthalpy changes of formation are shown in the table below. He will ask to calculate the standard enthalpy change of combustion of ethanol. So I find a lot of students have issues with these questions because it's asking for standard enthalpy change of combustion. However, they've given you the data, which is standard enthalpy change of formation. So a lot of people will approach this question, and this is going to be a Hess cycle question, using the wrong method. They will use the Hess cycle of combustion rather than the Hess cycle of formation, and that would be a massive misstep in this question. What we need to remember in any enthalpy question full stop, what determines the method that we use is what data we're given. And in this question, you can see that we're given the enthalpy change of formation values. So that dictates that we're going to use a Hess cycle that has the elements on the bottom so that we can use these enthalpy change of formation values. So I always like to start just by writing my balanced equation along the top. And this equation does happen to be a combustion equation. And that's where this enthalpy change of combustion is coming into it. You've got the enthalpy change of this top reaction. Now, because we have formation values, I'm going to write elements along the bottom. I'm not going to take the time to write down the individual elements. That's a waste of time. Remember that this Hess cycle is just a learning aid. It's just an aid to solve the problem. It doesn't have to be exact, okay? So now I'm going to do my arrows going up because those elements make those things at the top. And now I'm going to complete in the relevant enthalpy change of formation values. So as you can see up to this point, I've got the minus 269.3 written on the left-hand side to show the formation of ethanol. Then over on the right-hand side, I've started by saying 2 times minus 393.5. And that's because we have 2 carbon dioxides that we need to form. Remember that enthalpy values are always per mole. So if we have 2 of something or 3 of something, we need to account for that. So next up now, I'm going to add to that 3 times the minus 285.8 for the water. And to make my life easier later down the line, I'm going to tally up the values on that right-hand side. So I'm going to put into my calculator 2 times minus 393.5 plus 3 times minus 285.8. And that gives me minus 1,644.4. So now I've got my completed Hess cycle here. To use this, let's not forget what a Hess cycle is all about. What it tells us is that the enthalpy change is the same regardless of the route taken. So in this case, we want to find the enthalpy change of this top reaction going from left to right. And we could go directly, but we could also go down to the elements and then up to those products. And so that's what we're going to do. Let's start by going down. Now notice that's the opposite direction to the pink arrow. So we need to reverse the sign of that negative 269.3 and we make it positive. Then we want to go up from the elements up to those products. Now we're following the same direction as that pink line. So we're just going to write it as we see it, that minus 1644.4. And that's the calculation we need to do to find this enthalpy change of combustion. We need to do positive 269.3 minus 1644.4. Now, tapping that away into the calculator, I find that this enthalpy change of combustion is equal to minus 1,375.1 kilojoule per mole. This calculated value is different from the experimental value. Here we're asked to give 2 reasons why there's a difference. So here we need to consider what might have taken place in this experiment. So there's a chance that perhaps incomplete combustion took place. Now, when there's incomplete combustion taking place, obviously a slightly different reaction is occurring, and so we'd get a different enthalpy change. So another possibility is that when this experiment was taking place, it wasn't actually carried out under standard conditions. Remember, we calculated the standard enthalpy change of combustion, which means that that is the standard value under standard conditions. Now, the final possibility for why the experimental value might be different to the calculated value is that some heat may be lost to the surroundings in an experiment. Now, this question only needed 2 reasons, so you can state any 2 of those. So now we're asked to sketch an enthalpy profile diagram for the complete combustion of ethanol. Here we're asked to label the enthalpy change of reaction, give the formula of the reactants and the products, and the activation energy. Now what we need to know here is that in a combustion reaction, we have an exothermic process. Now, when we have an exothermic process, we're going to place the reactants higher than the products. So the reactants in this case we know are C2H5OH plus 3O2, and we know that the products are 2CO2 plus 3H2O, and the reactants are above the products. So now we do our little hump, okay? Now, when we look at this hump, when we go from our reactants up to the peak of our hump, what we have there is our activation energy. Now we want the enthalpy change of reaction illustrated on this diagram, and that is the difference between the reactants and the products. Now in this case, the direction of our arrow matters. We need to go from the reactants to the products, and in that case that's going to be an arrow pointing downwards, and we're going to label that delta H. Make sure that all of your labels are clear so that you get every single mark in this question. Bismuth oxychloride is an ingredient regularly found in cosmetics as it gives a pearlescent glow and sticks well to skin. BiOCl is made from the reaction of bismuth trichloride with water. The reaction is shown here. Bismuth is found in group 5 and forms similarly shaped molecules as to the other group 5 elements. Here we're asked to draw the shapes of bismuth chloride and water. So the way that I like to do this is to start off by just doing a dot and cross diagram really quickly for each of these. So bismuth chloride, I know it has 5 electrons and it's bonded to 3 chlorines. that means that when I draw this structure, I'm going to see that I have 3 bonded pairs with the bismuth and 1 lone pair. Now, I've learned, and you need to as well, that when we have this combination of 3 bonded pairs and 1 lone pair, we have a trigonal pyramidal shape. And so that's what we need to draw here. We're going to have the bismuth with a lone pair on the top, and then we're going to have 3 sticks coming out of it, 1 into the page, 1 out of the page, and 1 sort of parallel to the page. And the shape of that is trigonal pyramidal. And the way that I know that is just by knowing that that's the shape when we have 3 bonded pairs and 1 lone pair around our central atom. So now let's do the same thing for water. I know oxygen's in group 6, so it's got 6 electrons and it's bonded to 2 hydrogens in water. So we're going to have here 2 bonded pairs and 2 lone pairs around that oxygen. Now, when we have this, I know automatically again the shape that that will have. I know that that gives me a bent or non-linear shape. And so that's what I'm going to draw. So I just have 2 sticks just going out parallel to the page and 2 lone pairs on that oxygen as well. And I can describe this as a non-linear shape, a bent shape, or an angular shape. But it's really just a 2-dimensional molecule here because it doesn't have that 3rd stick to make it 3D. So there we have the 3D shape of the molecules bismuth chloride and water and the names of their shapes. Here we need to suggest a possible bond angle for the BiCl bond in BiCl3. And we're asked to explain our choice. Well, to do this, let's just remember bismuth is of course in group 5, so it has 5 electrons. 3 of those electrons go towards making these bonded pairs of electrons with a chlorine, and 1 is a lone pair. So we know that this is trigonal pyramidal shape. We should know that when we have a trigonal pyramidal shape, we have a bond angle of 107 degrees. And so that is our answer here. So we need to explain this though, okay? We don't just want to say it. And I really like these questions because they're quite methodical. We just want to state the number of bonded pairs, the number of lone pairs, and then finish up with the fact that lone pairs repel more than bonded pairs. So in this particular case here, you can see that we have 3 bonded pairs of electrons and 1 lone pair of electrons. So the reason why we have a 107 degrees angle rather than the 109.5 that we had when we had 4 bonded pairs is because of simply lone pairs repel more than bonded pairs. The structure of that question is really common. They could ask it about other things as well. So if they ever ask you to explain why something has a certain bond angle, your stock answer is just to state the number of bonded pairs, state the number of lone pairs, and then just remember that fact that lone pairs repel more than bonded pairs. So now we're asked to calculate the equilibrium constant at this particular temperature for this reaction. So to do this, we need to remember the equation for Kc. And that's why I brought forward this equation here. Because remember, the general formula for Kc is the concentration of the products to the power of their moles, all times together, divided by the concentration of the reactants to the power of their moles. Now, because we're talking concentrations, solids aren't going to play a part in these equations. So that means that we don't use the BiOCl. However, what we will include is everything else. So as you can see, I've written here, Kc is going to equal the concentration of HCl squared divided by the concentration of BiCl3 times by the concentration of H2O. So there's our equation. Now to work out Kc, we just need to use the numbers in the table. So let's substitute those in. Here we're going to have Kc equals 0.62 squared divided by 0.26 times by 0.15. That gives us our Kc. So we're just going to put that into the calculator now to find to 3 significant figures what Kc is. Okay, so I end up finding here that Kc is equal to 9.86. Now there's no units in this case because there's 2 units of concentration on the top and the bottom of the Kc equation. So our answer here is just going to be 9.86 to the 3 significant figures that the question requires. A student was asked to prepare a sample of hex-2ene from hexane-2ol in the classroom laboratory via the elimination of water. So the equation for this process is shown below. We're told that the boiling point of hexane-2ol is 136 degrees C, and the boiling point of hex-2ene is 70 degrees C. Hex-2ene and hexane-2ol are not members of the same homologous series. Here we're asked to state what's meant by the term homologous series. So this is a great definition question. If you don't know it, then get your flashcards out now and let's make a note of it. Okay, so we should know that a homologous series is a set of compounds which have the same functional group, but each successive member differs by CH2. And what we mean by each successive member is we're talking about as you go from having 1 carbon to 2 carbons to 3 carbon, the number of hydrogens will also go up by 2 hydrogens each time. So as you go, for instance, from ethanol to propanol, then you will then go up by 1 carbon and 2 hydrogens. So those are our 2 key points that we need to be able to state when being asked to define what's meant by a homologous series. We should know that they have the same functional group, and we should know that each successive member differs by CH2. So now we've got the big one, the big 6 marker, where we need to describe a method the student could use to synthesize a pure sample of hex-2ene from hexane-2ol. Here we're asked to include all the details of the reagents and equipment required, and we can use a diagram if we need to. So I would say in this question there's going to be 2 key aspects to it. The first is just the method that we're going to use at all to make hexane-2ol, and secondly how we purify that sample. Because notice the question didn't just ask for any old sample, it wants a pure sample. Now because this is one of those 6-mark questions, we're not going to get 6 marks for 6 points. No, we need to make sure to get 6 marks we give a very full, logical method that covers both the synthesis side and our purification steps in its fullest detail. Well, let's get started here. Okay, so to begin with, we want to put our hexane-2ol into a round or pear-shaped flask. And to that flask, we're going to want to add an acid catalyst. Now this could be, for instance, phosphoric acid or sulfuric acid, but we do want to give a named example of an acid catalyst. So that starts us off here. Now we need to think about what we need to do next. So the next thing we want to do is to start to set up some reflux apparatus. We want to connect this to a condenser where water is going in at the bottom and water is going out at the top. This is a very important bit of information, so we either want to include it in our writing, or when we label our diagram, we want to make sure that we make it clear the direction of movement of that water. So the next step is we need to gently reflux this over a heat source. And we can add an extra bit of information given what we were told on the previous page. We were told the boiling point of hexane-2ol. So we can refer to the fact that we want to reflux above this boiling point of hexane-2ol. So we can be detailed here if we want to and say reflux over 136 degrees C. So once we've finished refluxing this, maybe we leave it for 15 to 20 minutes, What we now need to do is reset up the apparatus for distillation. And we're going to now slowly distill our hextuene that we've just made at its boiling point. Okay, remember that the general mixture that we have, it's going to have a mixture of a bit of hexene, a bit of hexantuol, that acid catalyst. Now we just want to distill it to separate the hextuene, and that's why we're distilling it at the boiling point of hextuene. And again, because the information was given on the previous page, we can specify that we could distill this at 70 degrees C. So hopefully you can see here that when producing this hextuene, we've got these two initial steps. The first one is going to be making it in the first place through this reflux, and then it's starting to separate it off from the rest of that hexantuol to then just get the hextuene. However, we've still got a bit of work to do to make sure that we have it pure. So now let's finish up this question by talking about how we're going to ensure that we have a pure sample. So the first thing we want to do is to add a neutralising agent. An example of a neutralising agent that we may use could be sodium carbonate. The importance of this step is to remove the acid catalyst. We don't want that, we want a pure sample of hextuene. Of course, when this neutralising agent reacts with the acid, it's going to form a salt and water, which we will still need to remove. So our next step now is to use a separating funnel. Now, the reason why we want to use a separating funnel is because we need to get this pure sample of hextuene. Now, when we added this neutralising agent, a neutralisation reaction took place, and we would have made some salt and some water. So what we're going to do is we're going to use a separating funnel to separate the denser aqueous layer from the less dense organic layer, that organic layer being the hextuene layer. So once we've now separated and we just have the organic layer, we want to dry using an anhydrous salt. So for instance, we might use calcium chloride in this case. So once we've done this and we have dried using this anhydrous salt, simply we want to redistill our substance, and by this point we should have hextuene. Hextuene shows stereoisomerism. Here we're asked to draw the structures of the E and Z isomers of hextuene. So to get started here, I'm just going to do a really rough outline of what hextuene looks like. I'm not going to draw all the hydrogens, it's just for me to visualise it. I know that the double bond is attached to the second carbon, so I've put that into the right position here. I'm going to fill in the hydrogens, and then I'm going to redraw this in a way that really helps me to do isomers. I'm going to imagine it's just like ethene. I'm going to forget what it actually is for now. So I'm thinking, well, what groups are attached to each of those two carbons of the CC double bond? And I'm going to draw it in my classic shape that I would draw ethene, because it's going to be so easy to do my isomers now. So on the first carbon, I can see I've got a CH3 and an H attached. On the second carbon, I can see I have a C3H7 attached and an H. So that is now something I'm very familiar with, and I can really easily recognise whether I have an E or a Z isomer, and I can easily switch it up to make the other. I know that for the E isomer, I know that my groups are in opposite orientations, whereas in Z isomers, they're in the same orientation. So looking at what I've already drawn when I did my rough sketch here, I've actually drawn the Z isomer, because both of the H's are on the bottom orientation. They're on the same relative orientation. So I'm just recopying that there. So now for the E isomer, it's going to look almost exactly the same, except those two H's are now in the opposite orientation. I'm going to draw them diagonal to each other. And it's as easy as that. I now have my two isomers. The yield for this reaction in the class from the laboratory is typically low, around 40%. The E isomer is more stable and thus favoured, with 85% of hextuene made being the E isomer. Here we're asked to calculate the mass of hexantuol required to produce 1.95 grams of E-hextuene, and we need to give our answer to 2 decimal places. Well, we're talking about hexene here, aren't we? Hextuene. So let's just quickly work out the MR of hexene. I know the formula is C6H12, so the MR of that is going to be 6 times 12 plus 12, which gives me 84. Just done that for now because I know it's going to be helpful. We're given the mass of hexene, we can use the MR to eventually find the moles. However, we need to make 1.95 grams of E-hextuene. We need to know how much in total hexene do we need to make then? Do we need to aim to make? And as 85% is going to be that 1.95 grams, we need to find out what 100% would be. And the way to do that would be to take that 1.95, divide it by 85 to get 1%, and then multiply it up by 100 to get that 100%, that original amount that we need to aim to get. So here I get 2.29 and a load of decimal places. As there's going to be quite a lot of calculations here, I'm not going to round too early in this calculation. So I'm going to try and keep as much information in these early steps so that I don't over-round as I move forwards. So here I can see the mass of hexene that I need to make. Well then let's work out how many moles of hexene we need to make. And we can use there our MR of hexene to do this. To find those number of moles, I'm just going to do moles is equal to the mass divided by the MR. So I'm going to take that 2.294 and so on and divide it by the 84. Now that gives me 0.027 and many more moles, okay? By all means do write down all of the information there because like I said, it is important not to over-round. Now let's clear a little space here. That's how many moles of hexene we need to make. However, we know that the yield is only 40%. So actually we need to shoot for the sky and aim to make even more than that. Because in the end, that's how many moles we want to make. As our yield is only 40%, we need to aim to make more. Okay, so we're going to essentially say that this 0.027 is equivalent to 40%. We need to know what the 100% is we need to aim to make. So if we take 0.027 and use the calculator value so that you haven't rounded it too much. So let's go with 0.02731092437. And let's divide it by 40 to get 1%, and then times it by 100 to get 100%. Now that gives us 0.068277. So that's the number of moles of hextuene that we need to make, or try to make. Now, hexanol and hexene, if we look to an earlier page, the first page of this question, we know that it's a 1-to-1 ratio. So, if we know the moles of hexene, we can work out the moles of hexanol. It's exactly the same. Then if we use the fact that the MR of hexanol, as you can see here, is equal to 102, we can work out the mass of hexanol that we're going to need to use to make this 1.95 grams of E-hextuene. And we're going to do that using our classic mass equals Mr. moles, or the MR times by the number of moles. And we have there 102 times by 0.068277, which, if we round it to 2 decimal places, ends up giving me a mass equal to 6.96 grams. And so that is our answer. That is the mass of hexan-2-ol that we need to use to make 1.95 grams of E-hextuene. Elemental analysis was run on a branched organic compound X and found to have the percentage composition by mass of carbon is 64.86%, hydrogen 13.52%, and oxygen 21.62%. Further analysis via mass spec and infrared spectroscopy was conducted and the spectra are shown below. We're told that the molecular ion is unstable and therefore does not show on the mass spectrum, but it has an MZ value of 74. So the question here asks us to identify X and to include the IUPAC name and structure. So, given the information that we know, the very first thing that I would do is aim to work out the molecular formula. And the way we'll do this is by first getting the empirical formula. So the mass of the carbon, or percentage by mass of carbon, is 64.86, hydrogen is 13.52, and oxygen is 21.62. So we're going to put in the MRs now. Carbon is 12, hydrogen is 1, and oxygen is 16. So this enables us to work out the relative number of moles. It's not technically the exact moles because we don't have the exact masses, just the percentage by mass. However, by doing this, we can say that the moles of carbon is found by doing 64.86 over 12, which gives me 5.405. Next up, we'll do the same for hydrogen. 13.52 over 1 is equal to 13.52. And then finally for the oxygen, we've got 21.62 over 16, which gives us 1.35125. So now that we've got the molar ratio, we're going to divide by the smallest of these to get the simplest whole number ratio. So we're going to divide all of these by 1.35125. And when I do this, I find that I have 4 for the carbon, I have 10 for the hydrogen, and I have just 1 for the oxygen. So I've got an empirical formula here equal to C4H10O. Now that's a really important thing to start with because now we know the empirical formula, we can find the molecular formula. So we're told in the question that the molecular ion is unstable, but that it has an MZ value of 74. Now that MZ value is equal to our MR. So we know that the MR of the molecular formula is 74. What we need to do here is to work out what the MR is of the empirical formula and to see how that differs. So if I tally this up, I end up finding that actually the empirical formula also has an MR equal to 74. Now that's great news because that tells us that our molecular formula is actually exactly the same as our empirical formula. So we have now already got our molecular formula. And this is where we can now start to have a look at our spectra to see how we can be helped. So when I now have a look at my infrared spectrum, I can see I've got quite a broad peak at the region of about 3,200, 3,300-ish centimetres to the -1. And what that suggests to me is that I have an OH group. On the other hand, I'm missing an important peak. I don't have a peak around the region of 1,750, and that tells me that I don't have a carbonyl group. I don't have a C double bond O group. Now, what this information all comes together to tell me is that this must be an alcohol. So I've got my molecular formula, I know it's an alcohol, and I also know it's branched. Now the fact that it's going to be branched tells me that I'm going to have a tertiary alcohol. So looking here, I know that I have 4 carbons. If I do 3 in a chain with a branch of a methyl group, and then also an OH group, then I have my branched organic compound X. So looking at this, I can name it. I can see that its longest carbon chain consists of 3 carbons, and it has a methyl group and an alcohol group coming off of its second carbon. So I'm going to call this 2-methyl propan-2-ol. And there we have our IUPAC name, our structure, and we have clearly identified X using the information available.
Oh, well done, lovelies. I'm really, really proud of all of your hard work.